Okay, great. All right. So let's mute you. Okay. Okay, so I'm just gonna put down some questions and then you guys can just think in your head. These are most likely the type of question that he usually asks. And this is true for both this class for all three exams, and then the next class for all three exams. He will always ask some qualitative question that would basically probe your big picture understanding of the topic. So this is what I'm preparing you guys for a little bit. Okay. Okay. So here are the questions. Um, so let's talk about the first question. Oh, actually, let's quickly go through the first question. So can somebody tell me like what's the you can put it in the chat as well. You don't have to use your voice. Like what is the oh, and by the way, don't use your notes for this. Try to keep it in your head because you always have to you can always put down more stuff onto the cheat sheet, right? So for now, just maybe on top of your head. Um, what's the basically what is the relationship between say the wavelength and the mass or the momentum? Yeah, what's it called? And yeah, usually these quantitative questions are very easy to answer. So it's exactly the kind of things that he would definitely ask. And you exactly right. It's just the de Broglie wavelength. So it's a very easy thing to remember, right? It's so what is the formula for the de Broglie wavelength? It's related a little bit to the mass, right? Good. Okay. Or you can so your friend here says P equals to H bar over lambda, which is fair. But I mean you can always write it as P H bar sorry, H bar over B P. But and I just want to mention that usually this things comes very handy with this formula. So earlier today we go through a few problems in the homework, and whenever we calculate some kind of energy, right, just remember that p squared over 2m is equivalent to potential energy, and so this formula, the de Broglie wavelength formula, goes very well with p squared over 2m. Let's just keep that in mind. Okay, and alongside with that, just note earlier today we also do some problems with more people joining. Some problems with finding expectation values of a state. Oh yes, yes. Sorry, my bad. Yes, this is kinetic. Sorry, because why is it kinetic? Because P is mv, right? And so P squared is m squared v squared over 2m is a half mv squared, right? Yeah, your friend is Capricorn. Sorry, I misspoke. Yeah, so this is Ke. Pe is gonna be dependent upon x, right? In the case of a single harmonic oscillator, it's going to be a half m omega squared x squared, right? So yeah, you're right. You're right. Okay. Um, earlier today we talked a little bit about how to use operators x and p hat to find basically average values or expectation values of states of n states inside of a harmonic oscillator. And so later on, I will post that video as well so you guys can watch. But it's mostly just like detail working out of problem 16 and how to use um, operators as a means of finding out expectation value without having to write a full basically the full operation out using bracket, basically, instead of using the full wave function. Okay, so let's go to question two. So what was the relationship between the x representation of a wave function and a p representation of a wave function? So can somebody tell me what is that? So let's say that somebody give you an x representation of the wave function. Let's go psi x, right? And we are dealing with a time independent case, so there's no time dependence. So let's say that you have this, and so they want you to find the p representation, right? This is the x representation, meaning you're describing the entire system based on what? Based on the variable of position of something inside that problem, right? Usually in our case is a ball or is an electron that is both a particle and a wave, right? So exactly the Fourier transform, right? So just recall, right? The Fourier transform basically allows you to convert the wave function that encapsulate everything that we know about system in one of the conjugate variables to translate it to a different conjugate variables. You use the Fourier transform. The Fourier transform with respect to that conjugate variables. All right. So you would have P, right? So usually it's the case of doing a Fourier transform fully of psi of x e to the I minus I p x, right? dp. Oh, sorry, dx, right? We get you p, and that gives you this. Oops. That gives you phi of p, right? And the inverse Fourier transform gives you back the psi, right? Now, this is also true for any pair of conjugate variables, right? And my next question is going to be about conjugate variables. But let's say that you have a representation called of a wave function, but strictly in terms of say energy, right? So let's say I have kappa, big kappa of t time, right? You can do a Fourier transform with respect to energy and time. In this case, yeah. So in quantum mechanics, you don't care about the inverse, the sign in terms of the inverse or the normal Fourier transform, because the reason is because you're dealing with a non-signal like thing. Because think about it, what kind of waves are we dealing with here, right? We are dealing with probability waves, right? So they are fundamentally physical by definition. They are probability of the ball being somewhere, right? So the inverse transform or the forward transform doesn't. It's just a mean of transferring between the two domains, of the complex conjugates. It doesn't necessarily means that it doesn't necessarily matter if we use the negative sign or the plus sign. Does that answer your question? All right. Yeah. Okay, so we have let's say we have a kappa t, right? It's a wave function of the entire system that is strictly like only dependent on time. If we wanted to represent it in some in a the conjugate variable, what kind of so okay, let's say that we do a Fourier transform, right? So what would let's say small k or small kappa be a variable of? So what's the variable? What's the corresponding conjugate variable with respect to time? E, right? E here is energy, right? Yeah, that's correct. Why is it energy? Why is it energy? Yes, absolutely. So this is a little bit of a trick to not just your question in this course, but also for all of your physics problems, is that whenever you are uncertain, no pun intended, whenever you are uncertain about your answer to a problem, check the units. Basically, what your friend here is saying is that because we all know this to to calculate or to do math with, we all know this thing is the expression of the uncertainty principle. If you take a look at the units of h bar, right? What is the unit of h bar? The unit of h bar is literally energy time, right? But energy time, I'm gonna write this, okay? So this is the unit of energy times the unit of time, right? But the unit of energy and time is completely equivalent to the unit of what? Of position and momentum, right? So what this means is that if you can split, um, if you can correspond any variable that have the same unit as energy time and momentum position, you can those two variables whose products is equal to this unit are conjugate variables. Okay, and so that's what conjugate variable means. It means that the moment that you measure one of the variables to a certain degree, there will be a mismatch or there will be a compensation in the uncertainty of measuring the other conjugate variable. All right. And so it could be energy and time, it could be momentum and position. Another example is that it could be the number of photons, right? And phase. Okay. Now this description is another manifestation of the Heisenberg uncertainty principle, but in the realm of optics. Okay. And so this is just another example. So yeah, so and this could also be a qualitative question, like if he asks you what is the conjugate of a conjugate pairs of variables, you can say energy and time, or you can say number of photon and phase, right? That works. Okay. Okay. Let's go to the third question. Okay, so I think I already give the answer to this away, but what is the like physical meaning uh of the Schrodinger wave function? Like, can somebody just put it in the chat box? Let me. Sorry, just give me a minute. Square root of the probability distribution. Okay. Any other things? I mean, that's a very mathematical way to put it, right? You have, so we're doing question 4, by the way, for those of you who just joined. Yes, of course, the probability. Oh, sorry, we're doing 3. Sorry, we're doing 3. Yes, my apologies, guys. Okay, we're doing 3. So 3 is what is the physical meaning, right, of the Schrodinger wave function. Now, your friend correctly points out that it is the square of the probability distribution. Yes, yes. Okay, so there's three answers, but I think the correct answer is actually a superposition of all 3. Okay, no pun intended. So what it truly means is that it is true that it is something that evolves with time and with position. But in the case of our discussion in this course, mostly it's going to be time independent, so it will not evolve with time, but it will evolve or it will change with position. It is true that it is a square root of the probability distribution, but that's like more like a hindsight thing. What it truly is that it's not necessarily describe the particle location, but it's partially represent the it almost is the probability of this thing appear at that position, because you have to square it to get it. But then if it looks like this, right? If you don't square it, what does this means? Like, what does the negative part means, right? Because if you square it, if you square this, let's say you have this thing, and if you square this thing, it will become, right? All the negative is gonna get flipped up. But you can understand the sinusoidal as a clue. You can say that it is like a imperfect probability distribution. It's not really a probability distribution, but it's an imperfect one. You can say that. And so that's what it means. And your friend correctly points out that it is truly the square root of the probability distribution, right? Because if you think about the probability distribution, it is the wave function squared, which is also can be described as the intensity of existence, right? It is imperfect because it doesn't necessarily tell you where the thing is, right? You know the wave function, but that is because you learn it from the theoretical point of view. Quantum mechanics, as people figure it out, doesn't have like a physics experimentalist in the lab will never understand fully what is the wave function of a system is. They can only measure the square of the wave function. So that's why I said it's imperfect because it is non-physical. It's not a real thing. You will write earlier because you point out that it is the square of the probability distribution, which is something that is physical, right? There's a difference between things that are physical. Exactly. It has no physical meaning. Okay, it's purely a mathematical construct. Okay, and a lot of students, especially in PY 451, which is first semester quantum mechanics, get this question wrong because they think that it is a probability distribution. No, the square is the moment that you square it, it means something. It means something physically. You can record physically what does physically means? It means that you can record it in the lab, right? There's no way that you can actually see or observe a wave function in the lab, right? And so it's basically have zero physical meaning. It's imperfect. It's not a real thing. Yep. You can see of it as a hint to the probability distribution, right? But then the negativeness of sinusoidal doesn't mean anything. That's why the entire wave doesn't mean anything. It has no physical manifestation. But the moment that you square it, it means it gives you the distribution that you also see in your interferometer in the lab, right? So just make sure that psi itself doesn't mean a lot of things. It's a purely mathematical construct. Okay, are we good with that? Okay, good, great. Yeah, I mean, the entire class is here. I might as well just go slowly. By the way, do not worry about the 8:30 mark. I can stay until 9. Okay, so you guys can ask any question you guys want. Please stop me in the middle to ask questions. Okay. Okay. So we're done with 3. So let's go with 4. I mean, 4 we already talked about, right? It's basically just the square of the wave function, so it gives you the probability density, right? And then the moment that you got this probability density, you have to times it by dx to get the probability. So a wave function, you square it, you get the probability density distribution, and then you have to times that by dx to find the probability that it would pop up in this little space called dx, right? In the case of a box, if we have a box that is only defined in this region, let's say 0 and L, right? There's a few conditions for such a wave function to exist. First, the wave function, right, at the two ends of the box, the wave function has to go to 0, right? Because if it's not going to 0 at the two ends, then the wave function might not be normalizable, right? And that leads to the fact that psi has to do what? has to give you 1, right? Oh, sorry, let's do dx. This is x, right? It is normalizable, exactly. Square integrate to 1. And this, right, itself, psi squared, is the probability density, right? Not just the probability, it's a probability density, right? Function. And then the moment that you, let's say that you want to find the probability of this such a wave, of such a particle to be found in in between L1 and L2, right? Oops. I'm between L1 and L2, then what you have to do is you have to do what? You have to take the integral of psi squared, right? And then what? Oh, well, dx, of course, right? From L1 to L2. Okay? So that's what it means. And this is the probability that you observe the ball or the electron inside of this box between L1 and L2. We good? Okay. So this is just a recap, but usually people who are bogged down with like doing a lot of math work usually forget some of the basics. Okay, so that's it. Okay, so tunneling. So I have a question on tunneling. Um, what does tunneling means? And a more important question is, can the ball exist inside of a finite barrier? Okay, so that's my question. So what do you think, chat? Man, I sound like typical gamers on Twitch. Yeah, drop your answer in the chat. What do you think, chat? Can somebody just describe quickly what tunneling is? And can the electron exist inside of the barrier? Let's say that I have a barrier, right? So let's do question 5. Let's say that I have a domain, start from 0, end at L, and there's a barrier here, right? Barrier from L1 and L2. Now the barrier has energy V naught, right? And you have a wave. Of course, this is the probability density distribution, right? Inside and outside. Okay, so one person says can exist in the barrier. It does, but you can't really measure inside a barrier. Okay. Any other ideas? One more idea. One more question. Oh no, one more message, and then I'm gonna explain. Okay. Well, the truth is actually can exist. Yes, yes. So Andrew and Zhang is you guys. I think you guys think that it's might not be able to. You guys are technically you guys are not correct, but I know that's why quantum mechanics is very weird. If this is a finite, okay, so we're talking about finite, right? Barrier. If it is a finite barrier, it can't. Okay. And the reason is because this is the probability distribution, right? Or probability density distribution. What it means by this is that the what the slope here or the exponentially decay slope, what it says, it just means that the moment that this particle is inside of this barrier, it has exponentially increased chance of not existing there. That's what it means. But that statement does not mean that it cannot exist inside of the barrier. There is this much, let's say that you want to find the particle in exactly this region, right? This region, right? This region, delta L, right? There's exactly this many chance of the particle existing in there. And to answer your question, Andrew, it will also be measurable. Exactly. It has to be somewhere, right? And it can also be inside of the barrier as well, right? Yes. Yeah. Jojen, right? Sorry, I'm sorry if I butchered your last name. You're right. Yeah. You can think of it that way. Yeah. Um, yeah. Yes. Yes. What come in must come out, right? And then this barrier is not nothing. It's something, right? Now, the story is completely different if the barrier was infinite. If you have the exact same system, but the barrier is instead is an infinite barrier, right? Oh, sorry. Right? That is a completely different story. Why? Because if it was an infinite barrier, then the decay is assumed to be non-existent. There's there's zero decay. It just goes straight to zero. They will never pass that barrier. Okay. Uh, if the barrier width is smaller than the particle, yeah, so it doesn't matter. What matters in a quantum mechanics problem or in a 1D or 2D or even 3D problem is how much energy does the particle has the moment that it hits the barrier. It doesn't matter if the size doesn't matter too much, to be honest. Yeah, the size doesn't matter because you're thinking about young slit double slit experiment, right? That's true. When you shoot an electron as a slit, and the more comparable between the size of the slit and the electron, the more diffraction there is, or the more wave-like behavior the electron will exhibit. But that doesn't mean that doesn't work in this case. This case, we only consider the energy. So let's say that you have uh, electron coming in like wave-like and also particle-like to a barrier. There can be two things that can happen. The barrier has a finite potential, right? Um, it can either go through via tunneling or it can not go through. When cannot it go through? Well, in this case, let's say that it has a finite barrier, right? So V naught, this is not infinite, right? The electron cannot come through if the decay goes to zero inside of the barrier. You understand? So let's say that it's decay, but it decayed too fast, or the barrier is too long. Therefore, it dies before it can go to the other way. So in this case, you will never observe anything on the other side, right? But if the barrier is let's say is only here instead of the original one, then yes, it can go and then it still tunnel out, right? Right. So does that answer the question, Jojen? Yeah, but it only works for a finite potential. So does this answer your question? When you say that, is it what you mean by like if the width is smaller than the particle or something like that? Because like technically speaking, the width of this barrier doesn't matter. Like it doesn't matter if the width is bigger or smaller than the volumetric size or the mass doesn't matter. What matters is how much energy does the barrier contains. In this case, okay, good, good. In this case, V naught, and how much energy does the particles comes in with, right? That's what matters, and that's what determines whether you can tunnel or not, right? Okay, but of course, if the tunnel if the barrier is thinner, it means that you can still go in decay, but then the decay doesn't reach zero yet. It can still come out, right? But if it's infinite, right? If it's infinite, then you can think of it as like a step function. It goes in and it goes straight to zero. Okay, so there's nothing here, and also nothing here, right? Nothing on this side, meaning nothing on this side, right? Nothing on the other side. No matter how long or how short the barrier is, right? And in this case, it's called total reflection. right? Complete reflection of this wave. Okay, are we good on this? Okay, okay, right. Okay, so let's go to question 6. What does it mean by quantized energy level? And okay, so first, what create a quantized like energy levels? And second, can you guys describe the structure of these quantized energy levels inside of a infinite versus a oh sorry, an infinite versus a finite square well? Like if you have an infinite square well, like that's okay. So your friend says bound states create quantization. Andrew, I think you might want to flip the two words around, man. I think you meant quantization create bound states. Because bound state is a manifestation of the quantization of energy, but quantization comes first. It's a natural law. Bound state is just our mathematical yes. So periodic boundary condition. So what do you mean by that? What do you mean by periodic? Yeah, so this is good. This is good. What is this? Can you explain more on the periodic thing? I'm just gonna go straight to it. Okay, so bound states are created by well, quantization. I mean, is created by the encapsulation of particle inside of a lack of well, so basically when a particle has less energy than it than a potential, it is trapped inside of the potential. And it's very similar to the case of when you have like a bowl and you have a marble and you put it inside of the bowl, the marble cannot get out because the bowl has a potential dip or literally like potential energy dip because it looks like a parabola, right? So because the ball doesn't have enough kinetic energy to be outside of the to basically to overcome this height potential dip, it's trapped. And this is exactly the electron inside of a square well or a harmonic oscillator. That's what it means. Quantized energy level just means that it's quantized because um, the energy levels are the solutions for our partial differential equation, which is the Schrodinger equation. Um, we mathematically put it in a formalism where the solution only allows the particle to get certain amount of energies, and that's why it's quantized. Okay. So it's due to the continuity of each side of the boundary conditions. Well, technically, yes. Technically, you have to. Technically, the boundary condition is continuous in a cycle, so you can say that it's periodic. But the reason I asked about the periodic thing earlier is that I don't want you guys to misconcept periodicity in system, because if you were to do the third part of this class, you will have to touch on multiple atoms next to each other. And that's when the term periodic boundary condition kicks in. Now is not the time to use that, actually. But yes, you're right. The boundary condition technically wraps around, so they kind of like periodic, right? But the word periodic boundary conditions means something very different in solid state, which you guys will learn later on this semester. So so hold on to using the word periodic right now. Just say that it wraps around. Like yeah, yeah. Okay. Okay. Can somebody describe for me the structure of the quantized energy levels inside of a finite versus an infinite square well? So let's say that I have an infinite square well. What's the spacing between it look like? What does the spacing look like? Right? So this is a finite one, and then there's one that is like infinite. This one is infinite, okay? And then this one is a finite one. So what's the difference, right? I mean, we know that it's like different levels, of course, right? But what's the difference between the spacing of the levels? Because I think he might ask this. I think it could be a very valid, it could very much be a qualitative problem, right? It's very easy to sketch, but you just need to know it. Okay. So I can go through it. Yes, good. So when it comes to yes, so your friend here, Andrew, is correct, is absolutely correct. Inside of a finite square well, right? All of the energy levels start from, I mean, all of the, I mean, when it comes to wells, we start off with a ground state, right? So we start off with a zero state all the time. But in an infinite square well, it will what? It will, the spacing between the levels will increase over time, right? So you can see that it's spaced out, right? And more. But for a finite square well, right, it will get closer. Okay. And so you have something like this is like a second level one, right? And oh, sorry. Yeah, maybe I want to emphasize this. So I want to do something like this. Maybe this is one, right? And then this is two, this is three, four, five, and so on and so forth, right? And why is it like this? It's because of the nature of the solution of the problem, right? You can add on the spacing infinitively more because it is infinite, right? The well is infinite. But then for the finite well, the closer, the more energy, or in physical term, the more energy your electron has, the less more energy it requires to escape the atom, right? You can see of this thing as like an the well. You can see the well as like an atom. The more times you excite the electron from its uh, lower energy valence shells to higher energy shells, the less energy it requires to finally get to finally free the electron, right? And just for completeness, let's if you were to look at this as an electron inside a hydrogen atom, then the total amount of energy that will lift it from the ground state to a free electron is exactly 13.6 eV. Oh, sorry. Yeah, 13.6 eV. Okay, so this is the amount of energy required to take an electron that is inside of a hydrogen atom and free it. Okay, are we good on this? Does that mean at high enough energy it will become continuous? Yes, absolutely. Right? Absolutely. So if you so all of these are technically quantized levels, right? So they cannot mix, right? Because all of these states are orthogonal, right? Meaning they cannot mix. But you are absolutely correct. When you look like the moment that you go up, right, you can see that all the energy get closer and closer and closer, right? And then when the electrons get out of the well, what happened? It become free, right? What does become free means? It's continuous now. It can take on any energy it wants, right? The electron can travel at any speed, and because the speed is continuous, it means that the kinetic energy is continuous, meaning that the entire energy of the electron is also continuous. So you're absolutely right. Yeah, at high enough energy, meaning that after it gets out of this bound state, it is no longer discrete in terms of quantumness. It lost its quantumness and it's become classical. Are we good? Yeah. No. Yeah. Harmonic oscillator does not have equal spacing. It's only looked like that in the book, right? But of course, it's different, right? No, it doesn't have equal spacing. No. So check it and let me know. Wait, hold on. Let me think. Okay, I might misspoke again. I'm thinking about something else. No, it does have. Oh, okay. So let me. Okay, yeah, that's what I mean. Technically speaking, it doesn't. In real life, it doesn't. But because you guys are studying the harmonic oscillator, so your friend is asking a very good question. In a harmonic oscillator, technically speaking, in real life, the energy. So in real life, a harmonic oscillator is usually something like a could be an electron trap inside an atom, but it's usually more like an electron trap inside of a fake atom, more like something like a quantum dot, which is a solid state structure that mimics the behavior of an atom. In real life, it doesn't. But because you guys are studying the harmonic oscillator in the book, and you guys are using a dagger to denote the ladder operator up, and then the a hat only as the like we were talking about earlier um, as the energy lowering operator. These operators are quantized energy that assume that all the energy levels in the harmonic oscillator is equal. So your friend Andrew is absolutely right. The moment that you increase energy from one level to another, you plus one half h bar omega, right? And so what that means, oh, sorry, plus one half h bar, plus three half h bar. Sorry. Yeah. Every time you do that, no, not sorry, plus h bar, plus h bar. The lowest energy has one half h bar, right? Every time you go up one level, you add a half, oh, you add one h bar omega worth of energy, right? These operators assume that all of the energy levels are technically the same. And your friend is right. All of the energy level inside of a simple harmonic oscillator or a quantum harmonic oscillator is equal. Yes. Are we good? Okay. All right. I'm gonna move on, but just remember this, okay? Okay. Great. So I think we are good with all of the questions for the I guess for the like qualitative possibly. Now I'm gonna go through question 18 and 19, like one of our friends was asking in the first discussion. And before I start, any questions on anything, or actually any question that is non-relevant, not related to anything so far? Because just ask me extra question, and I'm willing to answer after this as well. Hermitian operator related math. What Hermitian operator? There's a lot. So let's okay. So let's do it here. I'm just gonna quickly go through this. Okay. So give me 10 minutes. Hermitian operator maths. Okay. So the Hermitian operators. So all the operators that okay. So in quantum mechanics, what does it mean by Hermitian, right? The physical meaning is that all Hermitian operators represents an operator that gives you something that you can measure, that you can see. Okay. So I have a question for you. Does the um, so inside of a harmonic oscillator, right? Does a dagger Hermitian? Are they Hermitian or are they not? And another question is X or P or H Hermitian, right? Right? Are these Hermitians? So just quickly drop in the chat. Okay. Actually, I want to check something. Let's see. Let me check this really quickly. Hmm. Okay. So somebody already let me see. Yes. Two yes. Yes. Okay, we're playing with words. Yes. Okay, good. So you guys are absolutely right. Second, all these are Hermitian, right? Technically, it's very easy because the moment that you apply this to any state in the harmonic oscillator, you get something that you can view, right? This gives you what? Gives you the average value for x, right? This, oh, oh, sorry, this one is actually average value of x in the end state, right? Is the average value of p in the end state, okay? So these all correspond to something that you can measure, right? So they are Hermitian because they are associated with a physical observable. What about these guys? Are they Hermitian? Some of our friends says no. Uh, one says, so Andrew says they are Hermitian conjugates, correct? But why? What does that mean? Oh, this is very nice. I actually should go through this in a discussion section. Uh, that's very one. The I yes. Okay, good. Yes. Okay, good. That's what it means. Yes. So if you remember, right, so what they are is the reason that they are conjugate, right? In the form here, they are conjugate with respect to energy, actually, because one of them alter the energy of the state but by increasing it, the other one decreasing it. If you think of it in a way of the uncertainty principle, time is not in the picture, right? So the change in the energy here is in both directions. That's why they are conjugate, right? Um, yeah, so that would be the intuition behind it. That's why it's called conjugate Hermitian parameters. Yeah. Um, let me say this. Um, By the way, I have a question. So let's say that one of the qualitative question asks you, why can we use ladder operators for a finite or an infinite well? Okay, so first question, can we use ladder operators for those or can we not? And why? Can we? Can we use ladder operators for infinite or for finite wells? Yeah. So the problem is that yes, it's strictly speaking, if you're a mathematician and you have all the time in the world to calculate the analytical solution for every single well, then yes, you can. But it is not useful because we have no quantifiable metric in which that operator can be used to manipulate things because of the strict assumption that all the energy levels inside of a harmonic oscillator is equal. Using a ladder operators allows you or like stop you from using like overcomplicated math to represent the wave function and also to finally calculate the energy. But because the energy levels in the wells are not equal, and technically even if you know the full wave equation i.e., you also know the energy of each level, it is unwise to use ladder operators. And so the answer is yes, you can, but the true answer is no, you should not use that. That's why he's not taught. Okay, so yes, yes, this is partially correct. Okay, so without further ado, I'm just gonna go into question 18. I'm just gonna quickly go through it, and then I'm gonna show while I'm solving this, I'm gonna show you some tricks to solve this faster because I see some of the. So actually, a lot of people send me homework. For some people, I haven't sent you back any feedback because I have way too many homework to look at today. It's all come in yesterday, and it's just like one trillion. No, it's probably not 1 trillion. It's like 15 or 16 homeworks. I'll try to send you back the feedback by the end of today, but it's a lot. Okay, so sorry if I haven't sent you back any feedback yet. Just wait out. Okay, so let's do 18 really quickly. Okay. So another thing that is worth mentioning is that you should try to write down some integral laws, some basic integral laws. And I'm going to go into the laws very quickly into your cheat sheet because they are very useful. Okay. And so question 18 asks us to construct psi 1x and psi 2x, which is basically the wave equation of the first and the second state from the ground state psi naught of x using ladder operators, right? So we have psi naught, right, is equal to alpha for x half. I'm just going to use exponential instead of e to basically make it clear. Okay. And so the first excited state is what? Right? How did you represent the first excited state? Well, psi 1, right, is equal to what? Is equal to a, right? A plus or minus? A plus, right? Because note that I just want to mention this. If you do a minus, right, on psi naught is equal to what? Oh, somebody is telling us. Isn't it root pi? Yeah, it's root pi. Yeah. Is it root x or root? Oh yeah, it's root pi. Sorry. Yes. This is a factor. Sorry. Yes, you're right. Acting on side 0. Yeah. Just want to mention that this, if you were to do like a decrease operator on psi naught, it's gonna be what? It's gonna be psi naught. Okay. And if you do a minus operator on yeah. No. So the 0 here is the eigenvalue, not the wave function. Okay, so the eigenvalue is 0, meaning that it doesn't get decreased. The energy is as low as possible already, so it doesn't go anywhere, right? So let's say that you do a minus psi naught, right? Then the energy is 0. Yeah, but it's not, the wave function is not 0. The wave function is the same for the ground state. Okay. Okay. Let's do psi naught. Okay, so psi naught is equal to this, right? Which is what? Which is 2 alpha x times by psi naught, right? Which is the exact same thing here, the entire thing here, times by 2 alpha x. All right. Similarly, we apply, if we want to find psi 2, we do the same thing, right? To psi 1, which is completely equivalent to a dagger squared psi naught, right? Which is what? Which is just 2 for square x squared minus yeah, just this and then psi naught, all right? Where psi naught is this thing. Okay. So that's easy. So what's the question asked us in the second part? Where's the question? I didn't have the question. Just have my solution sheets. What does the question ask us on my thing? I swear I got it out and I don't know where I put it. The question sheets. Oh, here it is. Oh, here it is. Okay. So question 18 asks us to consider to check the orthogonality of psi naught, oops, of psi naught, of psi 1, psi 2 using explicit integration. So when okay, yeah, thank you. Thank you. I got it. I got it. Okay. So when they're asking about explicit integration, you should try to do some integration out. But what you also should do is to learn some tricks about integrals that you don't have to do a lot of math. Okay, so the first one is very easy, right? And actually, this is a trick. Usually, when they're saying, "Hey, can you show that this integral goes to zero or this integral doesn't exist?" There are two tricks that you can say. You can say that without actually writing it out. If you are like rushed on time and you don't have the time to fully write it out, the best way to get the maximum partial credits is to say, "Look, I know this. I know this product. I look at the product inside of the integral, and they are odd. And because they are odd integrals, and this integral is from negative infinity to infinity, therefore this integral is zero because it's odd and it's symmetric." Well, so what's the definition of an odd function, right? An odd function is a function that is symmetric with respect to the center, with respect to the origin, right? So you don't have to necessarily write out everything when they say explicit integral check. What you can do if you don't have the time to get the maximum partial credits is to say, look, this is odd, and because it's odd and it's evaluated over R, therefore it's zero. And a lot of professors will give you full credits for that. Some, if they say explicit, they will give you a lot of the maximum amount of partial credits because that's the correct assumption. Okay. Um, in our case, it's very easy to see that this right uh, is zero. Right. I'm just gonna write this. This is like negative infinity to infinity. Right. Exact same um, as doing. So there's I don't know the factor. There's some factor here. Oh, okay. I know the factor. I'm just lazy. The factor is basically this, right? It's I. Let's not make the funny mistake again. And then you have R, you have exp to the minus alpha squared x squared, right? To alpha x, right? This is definitely an odd function. It's an odd integram, right? So you don't have to fully do this out. Just say that this is an odd integram. You get full credit. Mostly full credits. Yeah. Is it alpha over 2? No, I don't think so. Is it? I don't think so. I think it's this thing, right? Because for psi naught you have one of those, and then for psi 1 you have one more. So you have this, right? Because for psi naught you have this, and then for psi 1 you also have this, right? So you have two of those. Yeah, but the moment you say that this is an odd integrand, and odd integrand, yeah, and just so for those of you who don't know what I'm talking about, that this is what it means. An odd integral is symmetric with respect to the origin, meaning that it always kind of like contain the same like um area on both sides of the y-axis. And what that means is that the moment you add m all up, it's gonna always be zero because they are symmetric with respect to the origin, right? The area is basically a mirror. It's a mirror with respect to the origin. And so they always be the same exact area, but because they are mirrored, they are in the opposite direction when you add them up using the integral, right? And so that's why they're always zero. Okay, so just note that this, okay, R of an odd integrand, right, is zero. Okay. And how do you know something is odd, right? If a function f of x, right, is odd times by a function of g of x, that is that is even, then it's odd, right? So odd, odd times odd is even. But if right, but then even, of course, even is even, right? But then if there's one odd and one even, it's always odd, right? And this is true for numbers, for real numbers, also true for functions. So the moment that you can spot an even function and an odd function, right, and they times together, the entire integrand is odd, right? And it's always zero. But we, as quantum scientists, doesn't need math tricks to know that this is definitely zero, right? Why? Why is it zero? Why does it have to be zero? Because they are psi 1 and psi 0 are orthogonal, right? Uh, well, in this case, yes, they're Gaussian, but it's not because they're Gaussian that the integral is zero. But the easier way to spot is that because we are talking about orthonormal states, right? All of these Gaussian are solution or eigensolution. Yeah, no, don't worry, don't worry. No, you're good, you're good. Because they are orthogonal states, right? They are psi. This one is in the ground state, this is the ground state, and this is the first excited state. All of the state, remember, in the well, in the square well, or in the harmonic oscillator, all of the state are what? Are orthogonal, right? And because they are orthogonal, it's equal to zero, right? Another way to say this is that psi naught, right? Psi 1 is zero, right? Exactly the same as above, right? We got this? Oh, okay. Okay, good. Okay, so that's how you do it. And similarly, for all the psi naught and psi 1, it's always it's always the case, right? Between psi 1 and psi 2, between all of the psi naught and psi 1 and psi 2, all of them are zero solely because of orthogonality, which in turns can be confirmed by the oddity, right? The oddity of the products of the integrands, right? So just note all of these down into your cheat sheet, and hopefully it will help you with solving this integral a little bit better. You don't have to fully write it out. It's very complex, and you don't have to integrate anything. Just state this, and you usually get the full points. Especially if it's a qualitative problem, just put like, oh, because it's odd, the entire integrand is zero. Yeah. Okay. Let's do 19. Okay. So this is 18. Let's do 19. Okay, so 19, we have to find xp, right? Oh, sorry, px. Yeah, what is it, xp? P of x. Um, so the average value of x, average value of p, average value of x squared, average value of p squared, right? For the nth state. So when it comes to this problem, we can do it the easy way or the hard way, right? The hard way is to say, okay, I have x operator is equal to x, right? And then I have some state and by the way, some teacher would try to trick you by giving you like the form of a like a y function that is like something crazy, something massive, and saying, oh, you use this and use p hat is equal to minus ih use these two operators, right, to solve this problem. And some student will be tricked in for Gaussian, can we say that, I mean, you have to explain it a little bit more, right? I think what you should say is that because Gaussian is normal, and because that's literally what it means. Like Gaussian is normal, and because they are normal, and because their mean is by definition coincide with zero with the mean, because yeah, Gaussian mean is zero. Therefore, um, well, I don't know. I actually don't know. I think you should explain it a little bit more, actually. I don't know how you would say it though. Um, I mean, everybody knows the Gaussian is zero. Yeah, yeah. For a qualitative question, that should, I think that should be sufficient. But like, if he asked that as like a follow up in a quantitative problem, then I actually not sure. But let's say that it was a extension for a quantitative problem, then what you can also say is like you can just do this and then you put a Gaussian here, right? And then you say no, yeah, and then well, yeah, this is what I'm not sure about. Like, I think it should be sufficient. Yeah, maybe. Yeah, maybe just a quick like one or two sentences about like the nature of the Gaussian. Well, that's something that is a lot of time, right? So, sure. I mean, you can definitely do that. Looking at the sheets I sent you guys before, you guys can absolutely do that. It's just that it might not be the best way to spend your time. But yeah, feel free to do that. Don't be too worried about not be able to do that. Yes, yes. You okay? So usually, if it's a Gaussian, then that x and p are zero because they are means, right? But then just note that x squared and p squared are usually not zero, right? Because those are fluctuation, right? So this is like a general rule when you're dealing with Gaussians or normally distributed um, distributions, which is the case that the mean is oftentimes zero because they are centric or they're central by definition, but the fluctuation, meaning the variance is not zero. Therefore, the standard deviation is not zero, right? Gaussian looks like this, right? Usually you care about this. Actually, it's actually called full width half max, right? And these are not zero because if they are zero, then um, the Gaussian would be a delta function, right? So they're not. Okay, yes. Okay. Sorry, I got a little bit distracted. Sorry. Yeah, but usually when teacher says, I have this operator X and P, and they are represented by these kind of like, you know, um, the T or X, and then he gives you some funny function of X here, and then as I solve this, never, never do the entire thing out because it would take you 3 decades to fully finish the problem. Instead, right, what you should do is use ladder operators, especially in the case of simple harmonic oscillator. All right, I have seen people who ask questions on simple harmonic oscillator, giving the students like psi one or psi zero, which is a ground state or first excited state, and then say, hey, use this to find the expectation value of this psi for x for not for x but like for p, right? And there are some students who would like say, oh, because p is this, I'm just gonna apply this to some crazy ass function, and then I have to redo the integral everything. That's crazy. Never do that. Okay. The first step to do is to use your bracket knowledge. Okay, and just say, you know what? I don't care. I'm just gonna write x hat, right, is equal to what? It equals to a representation, right? That I know is true, and it's a combination of a oh, of a dagger plus a normal, right? And you guys all go through this before, right? So this is h over two, and then this is a dagger minus a, right? So this is you are rewriting some operator in terms of the ladder operators, right? Now, if you were to want to calculate, let's say the first thing that we have to calculate, right, is x, right? Then this is completely equivalent to what? Well, for the state n, right? What we have is the average values of the position x in the state n is equal to the bra of n, right? The x operator, and then the ket of n, right? Right? Are we clear on this? Right? And then what? And then you substitute, right? X here onto that. H bar over square root of 2 m omega, right? And then a dagger plus a without dagger, and then ket, right? And then what do? So you know that this thing is just a constant, right? The mass doesn't change, the frequency is fixed, and the this is just a constant. So you pull it out, right? So we omega, and what you have is this thing, right? Right. So I'm just splitting this into that, and then splitting this into that, right? And then we're gonna say, hey, this, oh, sorry, this applied to n gives you what? Gives you what? Gives you n plus 1, right? This is still n. Oh, sorry. This side is still n, right? Because nothing has changed. Similar here, if you act this on this state, right? You have what? Oh, n minus 1, right? This side stayed the same. Note, okay, somebody have to tell me right now in the chat, right? Chat, you have to tell me right now. What does these two things evaluate to? 100 of what? 0, right? Yeah. All these are 0, okay? Because why? Because they are orthogonal, right? So all of them are 0. Therefore, that is this is also exactly why when you do only x, only x and only p, right? You get 0, right? Because what? Why is that the case? Well, because p, don't remember what is p? P is just some factor. It's called a factor a, right? A dagger minus a, right? This thing is no difference because imagine this, n a hat only, oh, and n, right? This thing is just n. This thing become what? Become n and n minus 1, right? And the same thing can be said about here, right? N and n a hat n. This thing becomes n plus 1. Oh, this is sorry. This is plus 1. This is negative minus 1. So that's why if you only do only p or only x, it will always be 0, right? Because you always lead up to an orthogonal inner product, right? But if we were to have x squared, right, or p squared, right, then the story is different because for x squared, of course, we have to square the what? Okay, so what do we have for x squared, right? We have this, right? X squared, right? N, correct? And then this one becomes what? N, some funky h bar over 2 omega m, right? Is it correct? Yep, right? Without the square root. And then what? And then a hat dagger, a hat dagger plus a hat 8 plus oh, a hat dagger plus a hat, right? And then the ket, right? Now, if you apply each of these one onto, oh, sorry, onto this ket, right? Because if you have to split them out into 4 terms, right? Four average term. Yes, x bar squared. Yes, yes. Okay, thank you. Um, because if you apply each of these into the n, what you will get is what? This one will give you n, right? And n plus 2. Because each of these, right, this one turns n into n plus 1. And then this one acts on it, n plus 1 becomes n plus 2, right? This one becomes what? N something, right? Right, something. This one evaluate to n. Well, okay, so all of these they have some factor at the start, right? So I don't want to mention the factor for right now. I just want to get the point through. Is that and this one gets you what? N and n minus 2, right? And because each of these is a demoting operator. So they give it, so the first one turns n into n minus 1, and then the second one turns n minus 1 into n minus 2, right? So as you can see, this thing, right, and this thing is completely zero because this is n, and they're in the product with a different state, a different orthogonal state. So it's zero by definition, right? This is also zero by definition, right? So the only thing that's left is our good friend the cross terms, right? And the cross term usually they give you this. Oh, not the best color, sorry. And for the problems when it involves like the square of x or the square of p in the context of single harmonic oscillator, if you reach something with this, it means that you are safe. It means that you can carry on that term onwards. It's not zero. Otherwise, it is zero and it's irrelevant. Okay. So in this problem, if we were to only consider, right? If we were to only consider the cross terms, and you can check it for yourself, p of x, right, at the n level is zero, but p of x squared at the n level is what? Is m h bar omega over 2 times by 2n plus 1 times. Okay? And you can cross-check this solution. Another one is, okay, so let's say that if they were to ask you for the uncertainty, right? What is the uncertainty? Just square this, right? Oh, yeah, I really do not like the automatic functionality of this app. Just square this, right? Because the square of the, so this is what? This is the variance, right? This is the variance in px, right? Square of the variance gives you the standard deviation, which is the uncertainty, right? In px, right? So this is variance. So the square of variance gives you the STD, not that kind of STD, which you don't want to get, STD of the statistic, right? Which is equivalent to the uncertainty, right? We got it? Okay. And so in the same fashion with x, we also have p, right? So x itself at the n level is zero, right? But if you do x squared, because of the cross terms, right? The cross ladder operator terms, you would get something like 2 h bar over m something m omega something. Let me see. Yeah, h bar over 2m omega, right? 2n plus 1. Now confirm this for me. Like, do it, like a lot of people already got the right answer, but for those who has not got the right answer, reconfirm it by using ladder operators, especially using this, right? To go through it again and make sure that that you get this two answers, okay? You get these two answers, all right? And then, of course, the standard deviation, STD of x, right? The standard deviation of x is what? It's the square root of the average, which not the average, but like the variance of x squared, right? Which is just the square root of this, right? Are we good? Are we good on this? Nice, nice. Okay, so those are the two things. Okay, and now to finish off question 19, right? You have these things. So you have the square root, right, of m h bar omega. Oh, sorry. Jesus Christ. By the way, my iPad is crazy hot for some reason. Mh bar over 2n plus 1, right? This is the what? This is the standard deviation of px, right? Times by the way, the standard deviation of px is exactly equivalent to delta px, right? Times by the square root of h. So we got it over here, right? Oh, 2m over 2m omega 2n plus 1, right? If we go through with this thing, what will we get? Right? We get, and this is, by the way, for the record, is the standard deviation of x, which is delta x, right? If we compute all of this, we'll get h bar over 2n plus 1, right? Now, now, does this satisfy the uncertainty principle? Yes, right? Yes, because it's satisfied because what is the lowest value for n? N has to be greater or equal to 0, right? The lowest energy, the lowest level is already satisfied. If n equal to 0, right, the entire thing equal to h bar over 2, which is exactly what we have as the minimum, right? If n is greater, oops, if n is greater, then it doesn't matter because delta px and delta px will always be greater than h bar over 2 times 2n plus 1 for all n greater or equal to 0, right? And this satisfies the Schoenberg, the Heisenberg uncertainty principle, right? So yeah, okay. So don't worry. Yes. So that's how you do it. All right. Um. Okay. So does that answer your? Okay. So yeah, Kala already got it done. Okay, so I'm after this session, maybe like, I'm gonna stay for another 15, 20 minutes to answer extra questions or to answer any question you guys have. I mean, you guys don't have to stay here the whole time, but you did anyway, so thank you very much. I hope you guys got some good sleep tonight. Don't stay up the whole night. Just do the exam tomorrow. Just get a good sleep first, and then you will pass the exam tomorrow. I guarantee it. Um, any other questions on anything before I'm gonna stay here for 15 minutes or 20 minutes for you guys. Yeah, no worries. For you guys to ask any questions. So I can do it on the board as well. Any other questions on anything? Trust me, bro. Like this exam is not gonna be hard. Trust me. The first exam not hard. The second exam slightly harder. The third exam is slightly harder than the first two, but none of them is gonna be hard. And oh, okay, I'm gonna zip it. Yeah. Oh yeah, I saw your email. You also, I mean, I also have a midterm tomorrow. I think if you're the guy who I recognize from class, yeah, I think you and I have the same exam for Paella, for photonics lab. So yes, are you ready for that as well? What exam you have tomorrow? No worries, no worries. I'm very happy to help. Yeah. Yeah, you guys, I mean, you guys don't have to say. I'm not going to go through any other question. What I wanted to cover is like a little bit of a qualitative questions to yeah. Oh, ECE lab. Okay. So is it like photonics lab? Because I'm also take photonics lab, so I have exam tomorrow as well. In the morning, and then yep. Yeah. Okay. Well, good luck with that. Yeah, I'm also very scared for that, but okay. I'm not scared. I'm just kidding. Okay. Any other questions? Yeah. Okay. Yeah. No, no problem. All right. Good luck tomorrow, guys. And yeah, let me know afterwards how you guys do on the exams. Hopefully, I'll be more helpful next time. Yep. Yeah. Yeah. No worries, man. Yeah, absolutely. I'm here to help. By the way, I'll post the video after immediately. Yeah. No worries.
I just have a question about the format. So
Okay.
it's usually like quantitative, like mathematical questions, right? And then he follows with the like
Qualitative
theory.
questions.
Yeah. He follows with like the theory after, right?
Yeah.
And cool.
Yeah. So usually he will give you three quantitative ones, and then one, two, or three qualitative. The quantitative is like 10 or 15 points each, and the qualitative is like 5 point each. And so the qualitative usually take up like 30% or 25% of the exam. The other 75% is similar to the homework.
Okay, thank you.
Yep, no worries. All right, guys, get some good sleep and let's fight tomorrow. All right, let's get these A's. Okay. Yeah, no worries, no worries. Glad to help. Okay. Uh, no, you guys. I mean, I think you guys are well prepared. You guys are super like attentive. So, yeah, I think you guys do well. Yeah, yeah. I know that some of you have two exams tomorrow. I recognize some names in the roster, and some of them are also in my lab. So, yeah. Oh yeah, thank you, man. Thank you. We'll see. Yeah, unfortunately, that class doesn't have any TA. So, yeah. Yes, yes. I'm also scared for yes, correct. Yeah, it's okay. It's okay. Um, well, yeah. If you guys have any other questions, you guys can still email me. I'll try to answer. Okay, so here's the deal. I have an exam tomorrow at 9 to 11. So what I'm gonna do is I will answer the question after 11 tomorrow. Okay, any last minute question, I'm gonna answer after 11 tomorrow. Before 11, I have to lock in. All right, so I can't answer right now. After this session, I have to lock in. So yeah, any other last minute question before I turn off the stream? All right, no, no worries. Yeah. So if you don't have any question, I'm just gonna turn off the stream now, and hopefully you guys do well tomorrow. Like, good luck, and let me know how you guys do it on the exam. All right. All right. Thanks very much for tuning in. I'll see you guys later. You guys can submit to me like a like your A's at the end of the semester. All right. All right. Cheers. Yeah. Have a good night, guys. Awesome. Yeah. Bye. See you later, Andrew. Yep. All right. All right. See you guys.